Hello everyone, today we will do continuation of shell momentum balances, and in particular we are going to finish our flow of steady state Newtonian fluid in a vertical tube. So let's just briefly review all of the concepts we will need to solve the problem. First, we have defined combined momentum flux tensor that basically has all of the momentum components that we need to consider. In particular, we have the hydrostatic pressure, this is a tensor version of it. So these two little lines underneath V denote a tensor. So in tensor view, my pressure is acting only in normal directions. So I have 1, 1, 1 on diagonal, and it's 0 for shear components. So this is always defined by a scalar, and this is how I put it together in a matrix that expresses the shear stresses, the stress components or momentum transfer in a particular direction across a plane that could be in a different direction. So that's why I need a full matrix 3 by 3 of those to define everything. And then I have shear stresses, tau. We will define them in a moment. And I also simply, so this is present only if the fluid is moving and there are differences in velocities, spatial differences in velocities. And then we have finally the convective part, which simply expresses the momentum that literally flows in with a different portion of fluid into my box. So if I go component by component, and this could be in any coordinate system, so I, J could be X, Y, Z, but that could also be R, theta, Z if I'm in cylindrical components. So all of these components, component by component, this is how expressed. So P is my molecular stress tensor, and it has a pressure component and dynamic viscous stress component, and then I have the convective component, which is simply rho v I v j. So those are my contributions. Now for Newtonian fluid, the way we find the shear stress is by looking at the gradients of velocity. This is again a tensor. This is Jacobian of a velocity field, which is a vector field. So I have all of the partial derivatives of all of the coordinate components of V inside here. And this is a transpose matrix. So mine, and mu is a viscosity coefficient. It also plays a role. So here I have divergence. So divergence of a vector is a scalar. So this is a number, and this is identity matrix. So we have 2/3 mu minus k. K is dilatational viscosity. So this is just a coefficient times divergence times identity matrix. This portion often is a 0 because for incompressible fluids, basically the statement of incompressibility for a constant density fluid is that divergence of V is 0. And we're going to prove that. We're just right now, for now, leaving it B and balancing only momentum and not mass. So this is my expression for tau for Newtonian fluid. Okay, and again, component by component, this is what I have. Now, if I'm gonna solve a problem, we will find a velocity distribution for steady state flows in this case in some simple geometries, because a lot of flow happens in tubing, which is cylindrical, in between two plates, and in annular flows as well as around spheres. So those are all relatively simple geometries. We will define a thin fluid element or shell in a coordinate system that is aligned with those solid surfaces that are bounding the flow as much as possible. And then we will say that rate of momentum change in steady state, that is a 0, is equal to rate of momentum coming in minus rate of momentum coming out, and addition of any external forces acting on my volume element. And then once we do that balance, we will let that volume element shrink and get a differential equation that we need to apply boundary conditions and solve. All right. So we have worked on a fluid in a vertical tube. So this is my tube of length L. I'm applying a pressure difference. So there's a P0 and PL here in a Z direction. And I have gravity acting in the same direction. So now I'm going to be in a cylindrical coordinate system. So nothing really changes as I rotate around because nothing really enters from the side of the tube. Therefore, I will not assume dependence on this angle theta cylindrical system at all. So everything will depend on the radius r, which essentially defines how far I am from the from these boundaries that are bounding the flow, and z because I have gravity and pressure, the pressure difference acting in that direction. So my relevant coordinates are r and z in cylindrical coordinate system, and theta we don't really consider in this particular case. These are some equations that relate to coordinate systems that we reviewed last time, and we assume in this particular problem, since nothing is coming in or out of these sides, the pressure, what's driving the flow is the potential difference in z direction. Therefore, I have only Vz velocity, and that Vz velocity, it depends on r, how far I am from the bounding surfaces, or rather from the center, which expresses a similar statement. So then we have Vr and V theta assumed as 0, so nothing is flowing out in radial direction, and V theta, which would be the rotating velocity, is 0 as well because I'm assuming a solid static wall. And then consequently my pressure is a function, my pressure is a function of only z as well. I don't have radial differences in pressure. All right, so last time we applied a balance on a shell. Now my shell is from r to r plus some very small value delta r. So this is from radius r to r plus delta r. So this is radius r plus delta r. And then I have thickness delta z, so I'm starting from a z coordinate z to z plus delta z. Okay? So this is my shell. It's like a little annulus. And I'm ignoring for now theta coordinate. So I don't have a slice of this in theta direction because there's nothing driving any flow in theta direction, so I'm not going to consider it. And we got busy basically balancing z momentum balance. We have phi, which is my combined momentum transfer tensor, and we are considering now for z momentum how z transfers across z plane, so this is in this direction, and how z transfers in r plane, which is in this direction. Okay, so when we balanced and we looked at all of the areas and we summed up all of the momentum that enters and leaves this a little shell, and we also gravity can change momentum within as well, so we take that into account. When we balance, we got the equation minus d dz phi zz minus 1 over r d dr of phi rz r. Okay? So we have actually now r times phi rz, which is expressing the fact that my radius and my area corresponding to a certain radial position is changing as my r is growing. That area is growing. So that's why it's multiplying this phi rz, and plus rho g is equal to 0. So this is the differential equation we're going to solve now. So let's get busy. First, we're going to remind ourselves that phi is P delta plus tau, so this is pressure plus viscous stress plus rho VV. What does this come down to for for different coordinate values. So we have PZZ, so that is Z momentum transfer across the Z plane, which is P times delta ZZ is 1, plus tau ZZ, plus rho VZ by definition of how we put together convective momentum transfer. So basically I have pressure plus tau ZZ plus rho VZ squared. Now tau ZZ involves derivatives in z direction of Vz, and we are assuming that Vz does not depend on z, therefore this is going to be a 0. So hence is not equal to partial derivatives, but if I have minus mu times minus 2 mu dvz vz, okay? So that's basically zeroed out. That phi rz is equal to tau rz plus rho vz-vr, and I did not add pressure components because I never have them in shear stress. So it's my identity matrix is 0 in this particular spot. So I have that this is simply equal to tau rz, because again I can also cancel this as 0 because Vr is 0. So this is tau rz. I'm going to leave it at that for this very moment. So I'm going to first solve for tau rz. So when I put my differential equation together, so I had minus ddz vzz, so minus ddz of p plus rho vz squared. And then I had minus 1 over r ddr of r times phi rz, and I'm going to actually immediately write down what that is. So that is r times tau rz plus rho g is equal to 0. Excellent. Now I'm going to also recognize that Vz does not depend on z. Therefore, partial derivative with respect to z of rho Vz squared will be 0. So what is left is I'm going to put tau rz on one side and everything else on the other. And when we figure out minuses in this, have that 1 over r ddr of r tau rz is equal to minus dp dz plus rho g. We will often refer to this as flow potential, or in terms of a flow potential. So I'm gonna, since the pressure is a function of z only, so this is dp dz, and I could write just fine dp dz. So I will interchangeably use partial derivatives and derivatives of single variables, because again we have dependence only on one variable, though this is a more general way to state this. So in any event, my PZ is going to be defined as flow potential. I'm going to get this color. P of Z minus rho GZ. So then this is, apologies, minus dp z dz. So this is my flow potential. So really it's just a shorthand notation for the pressure that includes both hydrostatic, thermodynamic component, and also thermodynamic component and hydrostatic, the one because of the weight of the fluid, okay, together into one sort of generalized pressure or flow potential. Excellent. So now I'm gonna, so what I basically have is that 1 over R ddr, R tau R z. And these are the tau R z are the shear stresses. So they're velocity derivatives. And my velocity depends only it involves velocity derivatives, but velocity really depends only on R direction. Okay. So, on the other side, I have minus dp dz, and this is a function of z. I'm going to recognize that this is a function of r. This left-hand side depends only on radius r. Okay? Because tau rz involves velocity derivatives, and the only velocity that actually has anything is the vz, and vz is a function of r only by assumption. And on this other side, I have a function of z. So I have a function of r and a function of z, and they have to be equal for all r and z. So to be equal for all r and z, to be equal for all r and z, this function shouldn't actually depend on r and z. This should be constant. And that's great because that's going to help me solve the problem. So both dp dz is a constant. So really the pressure will be a linear function. And my 1 over r ddr of r tau rz is a constant, and we're going to solve that for shear stress and ultimately velocity distribution. Okay, so that's what we're going to move on and solve next.